All right, so all this was from last time. I'll remind you where we were. We stated and proved the Rauch comparison theorem last time using the index lemma, which we finished the proof of last time. So we're not going to need the index lemma again until next week, but we will use it next week to prove the Morse index theorem. So we're going to start today with two applications of the Rauch comparison theorem. So I'll remind you what the statement is. We won't talk about the proof again. We'll do these two applications. Then we're going to move on to chapter 11. So we're only doing half of chapter 10, the first two sections, because the last two sections of chapter 10 involve material and isometric emergence from chapter 6, which we skipped, and it just generalizes this to more and more general situations. So I'd rather move on to chapter 11, which is the Morse index theorem, and then chapter 12, which is about the fundamental group. And then we'll see if we have time for 13. We probably won't get to 13 because after today, we have 5 more lectures. So this was the Rauch comparison theorem. It basically says if you have two Riemannian manifolds and you know something about comparing the curvatures, then you can compare their Jacobi fields. Okay, some books will call this the Jacobi field comparison theorem because they don't want to give credit to the author. So here's the setup. We have two Riemannian manifolds. They don't have to be the same dimension, but the one where I make these assumptions about conjugate points has to be at least the dimension of the original one. Okay, so this is k is at least 0. And we have geodesics with the same domain on m and m tilde respectively that are parameterized so that they have the same speed. And if we have two Jacobi fields, j along gamma and j tilde along gamma tilde respectively, they both vanish at the initial point. And they're both, the j prime, the initial covariant derivative, have the same length and the same component in the direction of the geodesic. So these three conditions on j and j tilde. And then we have to assume that the second guy, gamma tilde, has no conjugate points, and that the curvature of the second one is greater than or equal to the curvature of the first one only for two planes where one of the directions is the velocity of the geodesic, right? So only for a two-plane which contains the span of the velocity of the geodesic, we need to know that the curvature of g tilde, sectional curvature, is greater than sectional curvature of g on that. And then the conclusion is that the norm of j tilde is less than or equal to the norm of j for all times. Remember, we always got this from an assumption like this for small time using the Taylor expansion of this function. But this theorem says we get it for all time. And moreover, if these norms agree at some positive time, then these curvatures agree in the planes spanned by the velocity of the geodesic and the Jacobi field, they agree for all times, up to t naught. Okay, that was the statement. We worked very hard last time to prove it, so let's reap the rewards of that. So applications of Rauch. So the first one is going to be that we can get quantitative information on the distance between conjugate points, consecutive conjugate points, from bounds on curvature. So we're going to apply the Rauch comparison theorem in two ways for this proposition, which I'm about to state. But remember, conjugate points on a geodesic are basically where bad things happen, right? It's where the exponential map ceases to be a local diffeomorphism. And on assignment 4 in the first problem, you'll show that if you have a geodesic that has conjugate points, then after the first conjugate point, it's never minimizing anymore. You can always find a curve joining the initial point gamma 0 to the first conjugate point gamma of t naught, which has length less than gamma. Even if gamma is a geodesic, it doesn't always have to be minimizing. Okay, so here's the proposition. That M and G be Riemannian. I'm changing the notation from De Carmo. Suppose the sectional curvature K of G satisfies well, it's positive everywhere, but it has a strictly positive lower bound and an upper bound where 0 is less than R1, less than R2 are constants. So this, of course, it does not necessarily constant. It could be, but it doesn't have to be. It's a function. So what I say that this function is bounded between those points, I mean, if you take any point in M and any two plane at that point, the sectional curvature at that point of that two plane will be between these two positive real numbers. And let gamma be a geodesic on M, then the distance d between any two conjugate points, any two consecutive conjugate points, satisfies that it's between pi r1 and pi r2. Okay. So what do I mean by distance between consecutive conjugate points? A geodesic for us, it's really a geodesic segment, right? It has some initial and final point. We talked about what does it mean to have a conjugate point to a geodesic with a given domain, A, B, right? And it means a point is conjugate to the initial point if you can find a non-trivial Jacobi field along that geodesic which vanishes at those 2 points. So let's get the colors. If this is the initial point of the geodesic, and then this point is conjugate, that means there's some Jacobi field, normal Jacobi field, which vanishes at the 2 endpoints on here. Okay, so there might not be any point conjugate to this guy, right? But you might have 2 points on this curve which are conjugate in the sense that if you restrict the geodesic to this interval, then this point is conjugate to this one. That means there's a Jacobi field, non-trivial Jacobi field along here, which vanishes here and here. Okay, so that's what we mean by 2 consecutive conjugate points. It means that there are 2 points on the geodesic, and you treat those now, you restrict the geodesic to be from there to there. And you're saying that the final point is conjugate to the initial point. And there's no conjugate points in between. That's what consecutive means. Okay. So this is saying that if you know the curvature is constrained, it has to be positive, and it's constrained between these two extremes, then the distance between conjugate points is constrained. In particular, if these get closer and closer to each other, R1 and R2, that means the sectional curvature is more and more tightly pinched, doesn't have much room to move, then these get closer and closer to each other. So if R1, I guess this is true. If R1 equals R2, then it's constant sectional curvature equal to 1 over this thing, R1, which is equal to R2. And that tells us that the distance between conjugate points is pi R1. But we already know that, right? Because when R1 equals R2, we get the sphere. So I'm being a little sloppy here because if it has constant sectional curvature 1 over R squared, where R equals R1 equals R2, then it's a quotient of the sphere. But one example is the sphere. And for the sphere, we know the sphere of radius R, right? And for the sphere of radius R, we know that the distance between conjugate points is pi R, because any point, the first, you take a geodesic emanating from a point, it's a great circle, and the first conjugate point is the antipodal point, and that has length pi R. Okay, so this is in the simply connected case. Okay, and this observation, it gives us the hint of how we're going to prove this, because we're going to compare this Riemannian manifold to the round sphere of a certain radius and use the Rauch comparison theorem. So let's let M tilde G tilde be Sn R1 GR1, where SR1 is the sphere of radius R1, and the round metric GR1 has a constant sectional curvature 1 over R1 squared, right? So we usually just talked about the round sphere of radius 1, but if you scale the radius to R1, that means you're multiplying the metric by R1 squared, and that means that the curvature gets multiplied by 1 over R1 squared. So and we know, let's see, so hence K tilde is 1 over R1 squared is greater than or equal to K. Right? That's our hypothesis. I'm only looking at this part of the hypothesis for now. This part is going to give me this part, and the other one is going to give me this one. So we want to apply Rauch comparison theorem, which unfortunately is going to have to be erased, probably. So we need to make sure that, so we have condition B. We have B. Did I call them A and B? Yeah, no, I called them 1 and 2. We have 2. We also have 1 because, let's go over here. Let's let gamma be a geodesic on M, normalized. So its length is L. And let's let P be gamma of 0, and let J be a normal Jacobi field along gamma with J of 0 equals 0. And let's let P tilde be any point in M tilde, which remember was the sphere of radius R1, and let gamma tilde be a geodesic for this Riemannian manifold with initial point P tilde, and let J tilde be a normal, so again, normalized geodesic. So they have the same velocity because they both have speed 1. Be a normalized, normal Jacobi field along gamma tilde with J tilde of 0 equals 0. So remember, if it's a normal Jacobi field, we get that J prime gamma prime is 0 on the whole interval. That was from our characterization of not J prime, J. And this means that J tilde gamma tilde prime is 0 on 0L. Try to make that a second. What did I say? Condition. J prime. I think I have to go back and use the fact that this implies that J prime of 0, gamma prime of 0 is equal to J tilde prime of 0, gamma tilde prime of 0. So if you go back, why is this true? This was because in the properties of Jacobi fields, that's right. because it vanishes at time 0, and because, yeah, this guy implies that, and this guy and this guy. Right? We did this a few lectures ago. It's because you can write the function, this function, you can write it as this function is a constant plus a constant times t, and the constant term vanishes because of this, and the linear term is exactly t times that. Okay, so because these are both 0, we get that these are equal. And also suppose that j tilde prime at 0 has the same norm as j prime at 0. Okay. I can certainly do this by scaling. I'm a little bothered by this. In fact, this is 0, right? This is 0 because it's a normal Jacobi field. But anyway, and suppose this. Now, since gamma tilde has no conjugate points on 0 to pi r1, because it's a sphere of radius r1. We know that the distance between any two consecutive conjugate points is exactly, in fact, pi r1. That means that j tilde of t is positive on 0 pi r1. Okay, because it's a non-trivial Jacobi field. It vanishes at time 0. If it vanished anywhere smaller, we'd get a contradiction to the fact that we know the distance between conjugate points on the sphere is exactly pi r1. So we can apply Rauch. So this gives 1. Well, let me say it this way. So let d be the distance between consecutive conjugate points on gamma. Then the Rauch comparison theorem tells us that that j of t is at least j tilde t, which is positive on pi r1. I'm sorry, I'm doing, this should have come first, right? And then this comes after that. The Rauch comparison theorem, I can apply the Rauch comparison theorem to this setup. And because this is positive on this interval, j is at least, the norm of j is at least the norm of j tilde. That's what Rauch comparison theorem tells us. But since this is positive, that means this is positive here. So d is at least pi r1, right? Because if it wasn't, if d was less than pi r1, then this would vanish. But this is positive. So we've proved that this bound implies this bound. And now the other direction is basically reversing the roles of the two manifolds you're comparing. So now let M reverse the roles of M and M tilde. So what do I mean? Rm, let Rm G in the proposition be the M tilde G tilde of Rauch, and let the Mg of Rauch be the sphere of radius R2. Okay, then this has sectional curvature equal to 1 over R2 squared, and that's less than or equal to the sectional curvature of our manifold M, which is now what we're calling M tilde in Rauch's theorem, right? So I've erased it, right? The manifold that we're studying has sectional curvature at least 1 over R2 squared. So we're going to make that the guy with the no conjugate points, and then use M in Rauch's theorem to be the sphere. Suppose if the distance d is bigger than pi r2, then we can apply Rauch to this situation. Because remember, we need the geodesic on the right-hand side, on the m tilde, to have no conjugate points. We can apply to this situation on 0 to pi r2. Okay, so what am I saying? If we look at these geodesics and we let L be pi r2, then we're supposing that the distance between consecutive conjugate points on the original manifold mg, which is now called m tilde g tilde, we're assuming that distance between conjugate points is at least pi r2. So that means the geodesic gamma tilde has no conjugate points on this interval. So I can apply the Rauch comparison theorem, and this says that SNR2 has all of its conjugate points after pi r2, and that's a contradiction because we know it's exactly pi r2. Okay, hence d is at most pi r2. Okay, so you basically use the fact that we know exactly what's happening on spheres to show that using the sphere on one side or the other, we get the result. Okay. So as I said, this tells us that if the sectional curvature is tightly pinched, if we know that it's constrained between two positive values that are close to each other, then the distance between consecutive conjugate points on any geodesic gets closer and closer to a constant. Okay, any questions about that one before I do one other application? Okay, so application 2. This one's a little interesting the way it's proved. We estimating the length of a curve from an estimate on the curvature. So more precisely, I'm going to state a result now. It basically says that the more curved your manifold becomes, the smaller the lengths of the curves. And you can imagine that if you take a sphere and you have some curve, and if you now scale that so that scale it up, the metric up, that means the curvature. Sorry, if you shrink the manifold, right? If the radius of the sphere is r, then the curvature is 1 over r squared. So if r gets smaller, then the curvature is getting bigger. It's getting more and more curved because it has to go around in a smaller distance, and the length of curves is decreasing when you have more curvature. So we'll see that more curvature implies smaller lengths. But we have to make this precise. What does that mean? Okay, so I think I need more than one board to write it down, the statement. So we'll use these two and keep it on there until we've proved it. It's the following. So let's let M, N, G, M tilde, N, G tilde be Riemannian with the same dimension. The Rauch comparison theorem is more general, but both the applications we're doing are to the same dimension. Suppose K tilde is greater than or equal to K on M. So what do I mean? That means i.e. for all P in M, LP in TPM two-dimensional, and for all P tilde in M tilde and LP tilde two-dimensional in TP tilde of M tilde, we have that the sectional curvature of this guy is at least the sectional curvature of this one, right? So no matter which 2 points you're looking at and which two planes, the sectional curvature of M tilde will always be at least the sectional curvature of M. That's the assumption. Now fixed P and P tilde and a linear isometry iota from TPM to TP tilde of M tilde, which we can do because it's the same dimension, right? We have two inner product spaces of the same dimension, so they're isometric. Let epsilon be positive such that xp is a diffeo on B epsilon 0 in TPM onto B epsilon of P, and such that.
Could you close the blind?
Yeah.
It's quite bright.
Yeah. Yep.
Thank you.
Yeah. And such that xp tilde is non-singular, no critical points on B epsilon 0 on the ball of radius epsilon inside T P tilde of M tilde. So what does this mean? So no conjugate points to P tilde for geodesics emanating from P tilde. So no conjugate points in B epsilon of P tilde, right? So why is this? Because remember, we characterized conjugate points as exactly the points where the exponential map has a critical point, fails to be a local diffeomorphism. So we know we can shrink epsilon small enough so that xp is a diffeomorphism and xp tilde has no critical points in the ball of radius the same epsilon in TP tilde of M tilde, and therefore any geodesic emanating from P tilde in B epsilon of P tilde will have no critical points in this normal ball, right? It might have no conjugate points. Okay, I thought I could fit the statement. I think I can fit the statement. So for any smooth curve alpha into B epsilon of P, which is contained in M, define alpha tilde on the same interval into B epsilon of P tilde by the usual game we've played many times now. Alpha tilde is x P tilde composed I composed xp inverse. So this is why we needed xp to be a diffeomorphism from the ball of radius epsilon centered at P onto the ball of radius epsilon centered at the origin. You know what I mean? That's the diffeomorphism. This is an isometry, so it's certainly an isomorphism. And this now is smooth with no. We're gonna see that we need the no conjugate points. We need this part when we're going to apply the Rauch comparison theorem. So here, let's call the parameter s because we're going to have something else that's t for s in 0 to a. Then the conclusion is, I can just fit it, the length of alpha is at least the length of alpha tilde. Okay, so the one with more curvature is M tilde G tilde. So if it has more curvature, then its lengths are shorter. That's what this theorem is saying. But in what sense? In the sense that you start with one curve and you get the other curve using this identification. Okay, so any questions about this statement before we start the proof?
Yeah,
Okay,
like
so
why is it
yeah.
phrased in terms of two manifolds? You know, I would think if you were comparing lengths,
could-
it would be one manifold with two metrics.
Yeah,
And they'd
because
have
this is a more,
different
the question is why is it phrased in terms of two manifolds like this? Well, so you could, how would you make sense of this, right? If this was the same manifold in both cases, this would only be an
Mhm.
equality. So you could apply this to the same manifold, but then this would be an equality, and then you'd be getting the, you know,
Well, it would be, no, it would be
you
different
could take two
metrics.
different points.
Two metrics.
Oh, you could, yes, you could take the same manifold with two different metrics. That's right. But this is more general, right? Because this is a local result, and locally every manifold is just an open set in Rn. So that's why it's phrased like this. You could certainly apply it to m tilde equals m. But if you see the statement is purely local, right? It's just saying you fix 2 points in your manifolds, while locally they're going to be diffeomorphic to open balls in Rn with different metrics on them, right? So it is essentially a local statement.
Right. No, I mean, it's just sort of a philosophical point, but I mean, if you say it's one is more curved than the other, you know, it's like you're just comparing the metrics, not the spaces.
Yes, that's right. We're just comparing the metrics, and we're only comparing them locally. So it's really a statement about two Riemannian metrics on the same open ball, if you want. That's right. Okay. So what happened to my other eraser? Okay, so this is going to be another application of Rauch comparison, but it's going to be interesting how it's done. We're going to construct a particular parametrized surface as follows. So let's take alpha bar is going to be a curve in TPM, which is going to be given by alpha bar is exp p inverse compose alpha. So remember, alpha alpha was a curve from 0a into b epsilon of p, which is exp p of b epsilon of 0. Okay, so this is just looking at alpha, which is in starting at some point p. This is in b epsilon of p, and using the exponential map to write it as some curve through the origin. Doesn't have to be straight, alpha bar. And now for fixed s, consider the radial geodesic gamma s, which gamma s of t is exp p of t alpha bar s for t between 0 and 1. So in the picture, so this is the curve alpha bar. Let me draw the picture here, actually. Sorry. Sorry. I made a mistake here, because the curve alpha does not have to start at P, right? Alpha is just some curve in this normal ball of radius epsilon centered at P. So let me redraw the picture. This is deceptive. I'm used to all these curves starting at P. So P is the center of my normal ball, and alpha is some curve in here. And it's the image of some alpha bar here. And for every s, if I look at alpha bar of s, that gives me a vector from the origin to alpha bar of s in this b epsilon of 0. So I can exponentiate that and get, this is gamma s. Okay, so it's for this time s, for the parameter alpha, this point is alpha of s. I get a geodesic from P to alpha of s. That's what this is, right? This is the geodesic with initial point P, and final point when t equals 1 is going to be xp of alpha of s, which is alpha of s. So gamma s at 0 is P, and gamma s at 1 is alpha of s. Okay, and I can do this, of course, for any time s. So if I take some other time, I look at this thing, I'll get some other geodesic. So the family sigma, which goes from 0a times 0,1 into m, given by sigma of s and t, is this gamma s of t. So it's xp of t alpha bar of s, is a parametrized surface, right? It's smooth. And as we said, for fixed s, sigma of the map that sends t to sigma of st, which I called gamma sub s of t, is a geodesic, and therefore I have a variation. I have a family of geodesics. So if I look at d sigma ds at st, and I call this js at t, this is a Jacobi field along gamma s. Okay, because I have a family which at time s, at parameter s, gives me this Jacobi field. So if I take the derivative with respect to the parameters s, at s, I get a Jacobi field along that geodesic. And now let's look at the properties of this. So js at 0 is d sigma ds at s0, but that's d by ds at s of x p0 alpha bar of s. And this, of course, is just identically equal to p for any s. So this is 0. So we have the initial value of this Jacobi field is 0. What about at time 1? That's going to be d sigma ds at s1. So that's going to be d by ds at s of xp of 1 times alpha bar of s. And what is xp of alpha bar of s? It's just alpha. So this is just alpha of s. So if I take d by ds at time s of alpha of s, that's alpha prime of s. So we have that js at time 1 is alpha prime of s. We need one more calculation about this Jacobi field, and then we look on the other side, do the same thing. What about js prime at 0? Well, that's dt of js at 0. So that's dt at t of d by ds, sorry, dt at t equals 0 of d by ds at s of x p t alpha bar s. This is, remember, this is just sigma of st. So I'm just saying that a js is d by ds of sigma s, and then I want to take dt of that at t equal to 0. Well, we did this kind of calculation before. This by the chain rule, this is going to be xp star at T alpha bar S applied to d by ds of this, which is T alpha bar prime S. Okay. And now this is linear. So I can move this T out front because it's linear. And then when I take dt of this, there's going to be a term where I leave the T untouched with some other stuff, and I evaluate that at T equal to 0. So I don't care what that term is. And the other term is where I differentiate this T and just set T equal to 0 here. And when I differentiate this T, I'll get 1. When I set T equal to 0 here, I'll get xp star at 0 applied to alpha bar prime of S. And this is the identity. Okay, so this part is 0, and this part's the identity times alpha bar prime S. So what we've got is that JS prime 0 is alpha bar prime S. Okay, so we have these three things that I've circled. And now let's do the same thing on the other manifold. Similarly, to consider the parametrized surface sigma tilde with the same domain into M tilde given by, so sigma tilde of ST, it's going to be the exponential map at P tilde applied to T times I alpha bar of S, right? Because this has to be a tangent vector. This has to be in T P tilde of M tilde, and alpha bar of S is in TPM. But remember, iota is here, is a linear isometry. Okay, so I do this. And we're going to call this gamma tilde ST. Again, for each fixed S, T goes to sigma tilde ST, which we're calling gamma tilde ST, is a geodesic on M tilde emanating from P tilde, right? When you plug in T equals 0, you get P tilde. So therefore, I can differentiate, keep that, I can differentiate it with respect to S again, and I'll get a Jacobi field along gamma S tilde. So JS tilde of T is d sigma tilde ds at ST is a Jacobi field along gamma S tilde. And as before, we want to look at the initial and final values and the derivatives, basically the same calculation. So as before, we get JS tilde at time 0 is 0. It's the same calculation. So this will become xp tilde, and there'll be an iota here, but it's still a 0 here, so just p tilde. So this is the same calculation. JS tilde 1, let's just do this one. This is d sigma tilde ds at S1. So it's going to be d by ds at S of x p tilde of I alpha bar S, because now I'm putting T equals 1. So when I put T equals 1 into sigma of S and T, I get this. But remember the definition, alpha bar was x p inverse of alpha. So this is exactly alpha tilde. That's how we define alpha tilde in the statement of the theorem. It's x p tilde compose iota composed x p inverse of alpha. Okay, so this is alpha tilde, and then I take the time derivative at s equals 0 at s So that means that J S tilde of 1 is alpha tilde prime at S. Right? I'm comparing with this, same thing. But the last one's a bit different because of that iota. So J tilde S prime at 0 is dt J tilde S at 0 is dt at 0 of d by ds at S of x p tilde of t iota alpha bar S. And again, we use the chain rule here. This will be x p tilde star at t iota alpha bar S applied to the S derivative of this. Okay, and again, I can pull this through because it's linear. And again, I'm going to have some stuff times t evaluated at t equal to 0 plus x p tilde star at 0 applied to I alpha bar prime S. And this is the identity. So this is I alpha, this is 0. This is I alpha bar prime S. So we get J tilde S prime 0 is I alpha bar prime S. Okay, so I've got hopefully 6 equations here. Maybe I should just write them all out again. Oh, I shouldn't have erased that. So I have JS of 0 is 0. JS tilde of 0 is 0. I have JS of 1 is alpha prime of S. JS tilde of 1 is alpha tilde prime of S. I have JS prime at 0 is alpha bar prime of S, and J tilde S prime at 0 is I alpha bar prime of S. Okay. Now we apply Rauch. So we have to see.
Could you just
Yeah.
remind me where I came from? I guess I blanked.
I was the linear isometry between TPM and TP tilde M tilde.
The isometry. Okay, thanks.
Okay. This is the next thing I'm going to say. So since I is an isometry, we get that JS prime 0 has the same norm as JS tilde prime 0, because one of them is I times the other, and I is an isometry. Okay, so now we want to apply Rauch. We want to compare these two Jacobi fields. This is one condition we needed for Rauch. This is another condition we needed. There's one more condition we needed, which is the following. Notice that gamma tilde prime S at 0 is, remember, what's the definition of gamma tilde? Let's do this slowly. Gamma tilde of S of T was exp P tilde T I alpha bar of S, and gamma S was exp P T alpha bar of S. So this one tells us that gamma tilde S prime at 0, the initial velocity is I alpha bar S. And this one tells us that gamma S prime 0 is alpha bar S. So if I now look at JS prime 0, gamma tilde prime S at 0, gamma tilde prime 0, by this one is alpha bar, sorry, tilde. This one is I alpha bar prime S, and then this one is I alpha bar S. I is an isometry, so I get alpha bar prime S, alpha bar S. And then this is equal to alpha bar prime is JS 0, and then this is gamma prime S 0. So we've established, this one says that JS tilde prime 0, gamma S tilde prime 0 is equal to JS prime 0, gamma prime S prime 0. And that was the last condition we needed for the Rauch comparison theorem. So these three green things, I know the color doesn't really show up on the video. These three circled equations are the triple of conditions that we needed on the Jacobi fields. We have, if we go back to the statement of the theorem here, we have the condition on the sectional curvatures. This is everywhere we're assuming it. What we need is the condition on the conjugate points, but that follows because of our assumption on epsilon. So we can apply Rauch because epsilon was chosen so that no geodesic gamma tilde emanating from P tilde has a conjugate point in V epsilon of P tilde, right? That's this condition here that X P tilde was non-singular on the ball of radius epsilon. Okay, so we have the condition about conjugate points, we have the condition about the curvature, we have the three pairs of conditions on the Jacobi fields. So Rauch then tells us has no conjugate points. Thank you. The Rauch comparison theorem tells us that the Jacobi field with the tilde has norm less than the untilted one for all t from 0 to 1. Okay, but now let's unpack what this means. This one, so alpha tilde prime of S is equal to JS tilde at 1 from this equation here, and that's less than or equal to by this this inequality at time 1, JS at 1, but that is equal to alpha prime S. And now integrate both sides. And we get from S equals 0 to S equals A, we get that the length of alpha tilde is less than or equal to the length of alpha. Okay, so more curvature equals smaller length in this sense. That's what we wanted to prove. Okay. I need a breather. Any questions? Okay. So we're gonna switch gears again somewhat. But we're still studying the objects that arose. The proof of the Rauch comparison theorem used the index lemma. The index lemma was about this index form, which is the integrand in the second variation formula, at least when you have proper variations. And so this thing keeps coming up. And the next couple of lectures, the rest of today and probably all of Monday, at least, we're going to be working on chapter 11, which is the Morse index theorem, which studies this index form in detail. The index form, I'll remind you the definition. It's a quadratic form, so equivalently corresponds to a symmetric bilinear form on a space of piecewise smooth vector fields along a geodesic. So it's a symmetric bilinear form on an infinite dimensional vector space. So most of you probably know a lot about symmetric bilinear forms on a finite dimensional real vector space, a lot of their properties still hold in infinite dimensions, but not all of them. For example, we can't really, in any sensible way, talk about a basis. So, let me say a few words. Well, I want to state the theorem. I want to remind you what the index form is. I want to state the theorem, and then we're probably going to spend the rest of today just doing some general things about bilinear forms on potentially infinite dimensional spaces before we get to the proof next time. So the Morse index theorem relates the number of conjugate points on a geodesic segment counted with multiplicities. Remember, if we have a geodesic, I'm not finished the sentence. If we have a geodesic with some initial point, some final point, then we can say which points on that geodesic after the initial one are conjugate to the initial one. And those are points where the exponential map is singular, where the derivative, the push forward, has a kernel. And we said the multiplicity of that conjugate point is the dimension of that kernel. Okay, so if you fix a geodesic segment and you look at all the points conjugate to this guy, and each one has a multiplicity, which is a finite number. Okay, and so you can count each of these with their multiplicity. So if this has multiplicity 2, it counts as 2, and then 3. Let's say this is 3, and then this is related to. It's related. I say relates to the index of the index form. It's too bad that they call it the index form and it has an index. The reason they call it the index form is because the interesting thing about this symmetric bilinear form is its index. But what is the index of a symmetric bilinear form? The index of a symmetric bilinear form is the dimension of a maximal negative definite subspace. So there's a problem with this negative definite subspace, is that this doesn't have to be finite, right? If you take some infinite dimensional vector space and you take the symmetric bilinear form on it, which is minus the identity, right? Then that's, well, let's say, what do I mean? A bilinear form is not an operator. If you fix an inner product, let's say on this infinite dimensional real vector space, then symmetric bilinear forms correspond to self-adjoint operators. So if you take minus the identity, that's a self-adjoint operator, that bilinear form is negative definite everywhere. So the maximal negative definite subspace is the whole thing, and that's not finite dimensional. So this need not be finite. In general, if you just have some symmetric bilinear form on it, of course, if it's on a finite dimensional vector space, the index will be finite. But if it's on an infinite dimensional vector space, the index may not be finite. One of the outputs of the Morse index theorem says the index is always finite for this guy, even though it's a bilinear form on an infinite dimensional space. There's only the maximal negative. There's not a unique maximal negative definite subspace, but all of them are finite dimensional and they have the same dimension. That's what this thing is saying. And the dimension of that finite dimensional subspace, maximal negative definite finite dimensional subspace, is related to the count of the conjugate points with multiplicity. So I'm going to give a precise statement before the end of the lecture today. But before we do that, let's just talk about some generalities about symmetric bilinear forms. Some of this will be a trivial review for most of you, which is fine because we've had a rough few lectures in terms of technical stuff. But you probably haven't seen the general statement. So here's a digression. So let's let script V be a real vector space, not necessarily finite dimensional. And let's let B be a symmetric bilinear form on V. So what does that mean? It means it's a map from V times V to R, which is bilinear and symmetric. And then there's an associated quadratic form. Let Q be the associated quadratic form, which is defined by Q of V. So Q is from V to R, and it's defined by Q of V is B of VV, right? And you see that Q of is not linear. Q of lambda V is lambda squared Q of V. That's why it's called a quadratic form. And we can recover B from Q by what's called polarization. Because we're on a field where the characteristic is not equal to 2, you can check that B of VW is 1/2 Q of V plus W minus Q of V minus Q of W. Right? If you just write this as B of V plus W comma V plus W, this is B of VV, B of WW, expand using the bilinearity and the symmetry, and that's what you get. Okay, so given such a symmetric bilinear form, let's define some objects. Well, one object from it. So the radical of B, denoted rad B, is defined to be, is the subspace of V given by rad B is all of those vectors V in the vector space such that B of VW is 0 for all W. Okay, it's clear that this is by the bilinearity of B, this is a subspace. And I could have done this in the opposite order. I could have put V on the right because this is symmetric. Right? If it's symmetric or skew symmetric, your bilinear form, then the radical doesn't matter where you're putting it. If it isn't, then it does matter. Do Carmo calls this the null space. But you kind of can understand why, but I'd rather not call it that because null space is usually the kernel of a linear map. What's really happening here is that if you had an identification of V with V dual, like if you had an inner product, let's say a positive definite inner product that gives you an identification, then the radical is the null space of the kernel of the associated linear map. Okay, but usually for a bilinear form, this is called the radical.
Yeah, but doesn't V define a map from V to V dual?
From V to V dual, that's right, but it's not an isomorphism if there's a radical. That's exactly the point. So
yeah.
So B is called non-degenerate if and only if the radical is 0. And in this case, then the map that sends V to B of V dot is a linear map from V to the dual, and this is injective. Okay, so in the finite dimensional case, that means it's also surjective and it's an isomorphism. Okay, but we're not going to be using this identification with V with V star. So that's the definition of the radical. That's a well-defined subspace of script V. And otherwise B is called degenerate. If the dimension, if radical of V is strictly big, is not 0, larger. Let's let W be a subspace of V. Yes, that'd be. Let W be a subspace of V. We say that the bilinear form is positive definite on W, if and only if Q of W is positive for all W in big W non-zero. Certainly, if I put the 0 vector into the quadratic form, that's B of 0, 0, that's 0, right? But if I put anything which is non-zero, if I always get something positive for the non-zero things in W, we call it positive definite. We say B is negative definite on W if and only if Q of W is less than 0 for all W in W non-zero. And of course, I could take W to be the whole of V, right? So a bilinear form is positive definite on the whole of V if whenever you plug in a non-zero vector into the quadratic form, you get something positive, etc. And it's easy to see that if the bilinear form is positive definite or negative definite on the whole of V, it has to be non-degenerate. So it's clear if B is positive definite or negative definite on the whole space V, then B is non-degenerate. Non-degenerate. Okay. Let me tell you an aside just for your mathematical development, culture, whatever you want to call it, in case you've never seen this before. If V is finite dimensional, which won't be the case for us, but if it's finite dimensional with the dimension of V equals, let's say, n, then there exists a direct sum decomposition of the space V into the radical, which is well defined, sorry, radical of B, direct sum, let's call it W plus and W minus, where B is positive definite on W plus and negative definite on W minus. Now, it doesn't make sense to ask if this is orthogonal direct sum. There's no inner product here. Right? This is just a vector space direct sum. But although the radical is canonical, there's only one radical, this W plus and W minus are not canonical. W plus, W minus are not unique, but their dimensions are. So let's call P is the dimension of W plus, is the dimension of any maximal positive definite subspace. In other words, it's a if you find a subspace of V on which the bilinear form B is positive definite, and it's not contained in any larger subspace on which V is positive definite, that's called maximal. And there could be lots of these, and there will be lots of these, but they'll all have the same dimension. This takes a proof, and Q is the dimension of any maximal negative definite subspace. So this is I don't know why it's called that, but it's Sylvester's law of inertia. You can find it in any good linear algebra book. We're not going to use this because we're not going to be in the finite dimensional case. But you probably most of you have seen this, and the reason I wanted to emphasize it is because when we apply this machinery, this language of bilinear forms and radicals and all that, now to the index form on the space of piecewise smooth vector fields along a geodesic which vanish at the two endpoints. That's an infinite dimensional space. There's going to be a radical. There's no reason in general for the radical to be finite dimensional if V is infinite dimensional. I mean, you could just take the bilinear form to be 0, and then the radical is the whole of V. And there's no reason for there to be a finite maximal dimension of positive or negative definite subspace. Question? Okay. So what we'll find is that for the index form, the radical is finite dimensional, and there is a maximal dimension of negative definite subspaces. But of course, that's not unique. And there won't be a maximal positive definite subspace because well, we'll see that there's an infinite dimensional space on which it's positive definite. Okay, and the definition, the index of V is the dimension of a maximal negative definite subspace. So this need not be finite. This is the end of the aside here, right? In the finite dimensional case, everything works great. This need not be finite in general. Okay, so now I think what we have time to do is to define what the space V is for us and what the bilinear form is, and state the Morse index theorem, and we'll start going through the proof next class. Okay. So there's a couple of times in this chapter where Ducharme was really sloppy, where he basically writes down some corollaries with no proof because the idea is that it's obvious from what just happened before. And in one case, it is obvious almost. In the other case, it's definitely not obvious unless you're familiar with this linear algebra story in infinite dimensions. So I will fill in all the gaps. So here's our setup. Let gamma be a geodesic, and let script V be the space of piecewise smooth vector fields V along gamma such that V at 0 equals V at A equals 0. So they vanish at the endpoints. Okay, this is infinite dimensional. You can just see that very easily. Just take one element, one non-zero element in here, and then multiply it by some smooth function, and there's an infinite dimensional space of smooth functions. And consider the index form IA on this space V. So that means that IA of VV is 0 to A, V prime minus R of V gamma prime V dt. So this is the integrand, the integral part of the second variation formula for proper variations. Well, it's the integral part of the second variation formula, and it's the whole thing for proper variations. So it's the whole second variation formula, for proper variations. So this is obviously a quadratic form on this space script V, right? Because it's if I replace V by lambda V, where lambda is a constant, I'll get 2 lambdas out of here and 2 lambdas out of here. That doesn't mean just because it has that property that it is the quadratic form of a symmetric bilinear form, but it is, and that's because of the properties of the curvature. So this is the quadratic form of a symmetric bilinear form, which will also denote IA on V, given by, we're going to define IA of VW is 0 to A V prime W prime minus R of V gamma prime W dt. So first, this first term is obviously symmetric in V and W. This is symmetric in V and W because of the symmetries of the Riemann tensor. This is symmetric in VW by symmetries of R of Riemann. And you can see that if I now set V equal to W, I get this. So this is what I was calling Q of V in the general linear algebra discussion, and this is the B of VW. Okay, so we have this infinite dimensional vector space. It's the piecewise smooth vector fields along this fixed geodesic, which vanish at the two endpoints. And on that infinite dimensional real vector space, we have this symmetric bilinear form, which could have a radical. It does have a radical. That's one of the first things we'll do on Monday. And let me just state the Morse index theorem, and we'll continue from there on Monday. The index of this symmetric bilinear form is finite, which it didn't have to be in general, and it equals the number of conjugate points to gamma of 0, number of points gamma of t for 0 less than t less than a, which are conjugate to gamma of 0, counted with multiplicities. So this is strictly less than a, right? So we look at all, here's our geodesic, gamma. We look at all the conjugate points, except possibly the final point, may or may not be a conjugate point. We look at all these guys, and it will have a multiplicity. There's finite, we'll prove, it's not obvious. There's finitely many of these. Each of one of them, of course, has a finite multiplicity, and the sum of those multiplicities is the dimension of a maximal negative definite subspace of script V for this symmetric bilinear form. Okay, so that's what we're going to do on Monday. I think we can do it all on Monday. I might need a little bit of Wednesday. And then we'll look at applications of this. It's not immediately clear why this is useful, but if you think about it, this guy is telling you the second derivative, because the second variation form is the second derivative of the energy functional at a geodesic. We know that the first derivative of the energy functional at a geodesic is 0. It's a critical point. And the second derivative tells us, is it a local max or a local min or a saddle? So knowing the index, knowing the number of directions in which this can be negative, is telling you how many independent directions will decrease the length of that geodesic. Because remember, for geodesics, minimizing energy is the same as minimizing length, because one is the square of the other up to some positive constant. Okay, so the negative directions, the negative definite directions here are going to tell us to what extent this geodesic, even though it's geodesic because it's a critical point of the energy, it may not be even locally length minimizing, right? I mean, what do I say locally? It's a certain length. It may not be minimizing, right? There might be other curves nearby it That's what I mean by local here. I don't mean that the curve is short. I mean sufficiently close to that curve in the space of curves between those 2 points, there could be another curve with strictly less length, equivalently less energy if it's constant speed. And that's what this is telling us, is that once we prove this index theorem, it says that if you fix a geodesic, you can see already if there's no conjugate points, right? That means the index is 0. That's what this theorem is telling you. The index is 0. That means there's no non-trivial subspace on which it's negative definite. So that means there's no directions you can go to decrease the length or the energy. That means it is minimizing. Okay, at least among all nearby curves, it's minimizing. And we know that if the length of the geodesic is short enough, there won't be any conjugate points, because the conjugate points happen when the exponential map is singular, but the exponential map is a diffeomorphism at least for a small time, right? So for a short enough geodesic, this is recovering the fact, it's not the full argument, because it says that for a short enough geodesic, there won't be any conjugate points, so the index will be 0, so there won't be any directions in which the second derivative is negative. That means that if you move this curve to a nearby curve with the same endpoints, it definitely can't decrease in length. It doesn't mean there might not be some other curve very far away with smaller length, right? So this will only tell you about information about the local min or local max, local min of this, right? Okay, so I'll restate the index theorem, the Morse index theorem on Monday. We'll start the proof. We'll get to the applications. Probably will take us, most of next week.